In my previous demo video, we have seen the fundamentals of the probability. Now I'll be giving a quick demo of probability for deep learning. In the first cell, I just like before, like I install all the dependencies. In the next cell, I import the libraries and the setups. I also set up a random seed of 42. And in the next coming cell, sample space and events, I'll take die roll as an example. This cell defines the sample space for rolling a fade die as a set of outcomes 1 through 6. Then defines events such as rolling an event number or rolling greater than 4. Next, here I draw colored rectangles representing each die phase, highlighting which belong to each event. And next is this cell connects probability theory to deep learning by showing how a neural network's logics are converted into probabilities using softmax. Next, in the next cell, I compute the complement, union and intersection of two events A and B on a die roll and verify all the probability rules. Next, this is a cell draws a Venn diagram with two overlapping circles representing event A and B. Next is conditional probability of medical diagnosis. Here I set up a medical diagnosis scenario with 1% disease rate, 95% true positive rate and 10% false positive rate to show the outcomes of it. Next is a Bayes theorem. This cell applies a Bayes theorem to answer the key question. Given a positive test result, what is the actual probability of having the disease despite a 95% accurate test? The posterior is surprisingly low because the disease is raised, illustrating the Bayes rate fallacy. Next is visualizing the Bayes theorem with population breakdown. Here I simulate a population of 10,000 people and visualize how many fall into each category: true positives, false negatives and true negatives. Next is this cell computes the expected value of a fade die using a formula E of x equals to the sum of each value time in probability. In the next cell, I compute the variance and standard deviation of the die roll using the formula that averages the squared deviation from the mean. In the next cell, this cell connects the value to deep learning by showing that the mean squared error loss is exactly the expected squared deviation between prediction and the true labels. In the next cell, I introduce a Bernoulli distribution which model any binary outcome like a coin flip or a neuron firing. And here are the outputs. Next is Gaussian distribution. And this cell introduces a Gaussian distribution as the most important continuous distribution in deep learning. This is the normal standard deviation of it. Next, here I implement initialization by sampling weight for the from a Gaussian distribution with a mean 0 and standard deviation equal to the square root of a 2 divided the number of input units. In the next cell, I define the entropy function as the negative sum of probabilities times their log base 2 and applies it to a distributions ranging from perfectly certain to completely uniform. Next, I implement the cross entropy loss function and apply it to compare a perfect prediction, a good prediction and a bad prediction against the true label. Next, this cell implements a KL divergence which measures how different one probability distribution is from another. Next, here I demonstrate MLE by generating 100 data points from a Gaussian with known parameters and then estimating the mean and variance from the data. In the next cell, I stimulate the Bayesian interpretation of neural network training where weights have a prior distribution that gets updated after observing the data. After this, in the next cell, I plot both a discrete probability mass function for a die roll as a bar chart and continuous probability density function as a smooth curve side by side. After that, in the next cell, I plot a CDFs for both discrete and continuous distribution in a 2 cross 2 grid as we can see here. And then in the next cell, I use a Monte Carlo estimation to approximate the expected value of x squared for a standard normal distribution by averaging over many random samples as we can see in the output here. In the next coming up cell, I then stimulate mini batch sampling from a dataset of 1000 examples for use in SGD. Instead of computing the full gradient overall data, we randomly sample a small each iteration. In the next, I implement the reparameterization trick used in VAEs, where sampling from a Gaussian with learned mean and variance is rewritten as the mean plus a scaled standard normal sample. After that, in the coming cell, this exercise implements both a naive softmax that can overflow for large logits and a numerically stable version that first subtracts the maximum logit. In the next cell, I implemented standard cross entropy loss and then a version with labeling smoothing where the hard won hotel labels are softened towards a uniform distribution by small epsilon. Finally, I in the final exercise implements a dropout layer from scratch using Bernoulli sampling where each neuron is independently dropped with probability p during training. And that's it with this demo. Thank you.